A first-order differential equation. If a general solution to a first-order differential equation, the only additional information needed to define a unique solution is the value of the function at a single point, called initial condition. So a differential equation with an initial condition is called initial value problem. It has a unique solution called the particular solution to the differential equation. Okay? So we'll start. This starts off kind of like any derivatives, and then this lesson will branch off a little bit. And we just started. Right, so we're going to look at separable differential equations. Right, so separable differential equations can be expressed as the product of a function of x and a function of y. Okay? So here, for instance, we have what's called a separable differential equation. All right, so we have dy dx we know is the derivative. So the derivative is 2xy squared. What you're going to want to do is you're going to want to get the y's on the one side with the dy and the x's on the other side with the dx. And one operation you're allowed to do is multiplication and division. So you are allowed to multiply and divide to move terms. Okay? You're not allowed to add and subtract, but you can multiply and divide. All right, so here we have dy dx is 2x squared. And so if we multiplied both sides by dx, we would move the dx over. So all we've done to go from one step to the other step is we've just multiplied this side by dx and this side by dx. And then, of course, over here, this dx cancels. So in this particular lesson, we are treating dy and dx almost as terms themselves. So now we would have this. We'd have dy equals 2xy squared dx. But if you look, we've got a y mixed in with the x's, and he really shouldn't be there. So we'll just divide both sides by y squared, and then we won't have a y over there. Right, so here's how we got to the next step. Dy over y squared is equal to 2x dx. Okay? And if you don't like him written like that, you can write him like that. So it's probably a little easier if we write him like this. Now we have y to the negative 2 dy equals 2x dx. And now if you notice, we have a dy with a function and a dx with a function. What do you think our next step might be?
Put them all on the integrate them? Take the
integrate them. Okay? We're going to integrate them. Okay? So we're going to integrate one with respect to y and the other with respect to x. And now once I integrate, I can only have x's over here, because I'm not allowed to integrate and have y's mixed in with the dx, and I'm not allowed to have x's mixed in with the dy. So we integrate both sides. Okay, so if we integrate y to the negative 2 dy, that becomes negative y to the negative 1. And then if we integrate 2x, that becomes x squared. And so now we want to make this look a little bit more like an equation. Okay? And we've got this one in the denominator and this one in the numerator. And I don't know if you knew this, that if you have a proportion, what you can do is you can flip the proportion. So that means the y can come on top and the x squared would go on the bottom. Or if you like, you can think of the other way as multiply this side by y and multiply this side by y. And then the y's there would cancel, and now you've got negative 1 equals x squared times y. And then if you divide both sides by x squared, you end up with this equation right here.
It's the reciprocal and the opposite, right? Because that's
Yeah.
negative, the signs that.
Well, we left the negative over there. No, it didn't have to be negative because if we were to flip it, it has to be negative because, oops, there's a negative there.
Oh, okay.
So now we have our equation, y equals negative 1 over x squared plus c. And that is, we've now taken our differential equation and we've rewritten it as an equation.
So when you integrate it, you're solving for y at that point?
Yes.
Okay.
Yes.
So that's the...
So once we integrate, yes, we're going to solve for y.
That's the function family of functions?
Yes, that's the function of the family of functions.
And then once you plug in the point, you get the specific function?
Correct.
Or is it called the unique function? What's the name?
Particular function.
Particular.
Particular. Yeah. So over here, I'm just going to make sure it's clear how we isolated move the variables around.
Multiply by y divided by x squared.
Yeah. So here we just multiplied both sides by y. So we have y times negative 1 over y. There we go. Equals x squared times y. And so now we just have negative 1 equals x squared y. And then if we want the y on one side and the x is on the other, oops, no, the wrong thing moved. Of course. You stay, you move. All right, so now we'll just divide both sides by x squared. So now we have y equals, and it doesn't matter if I flip it over here, y equals negative 1 over x squared, but we do need a plus c. Okay? All of our equations here will get a plus c, right? Because we integrated. Okay, so this is an indefinite integral. Yeah. Okay. Yep. Yep. So don't forget c.
Russell, you got me on the AP exam, right?
Yeah, plus c.
Maybe you should just bring high c.
Is that cheating?
Probably. I don't know. I think if you wrote "don't forget C" all over it, maybe. I don't know.
Don't forget right above the C.
I don't think they'll mark you off for that.
I don't think Mr. Gutman would notice.
I don't know.
I don't think they'd allow high C. I don't think they'd let you have high C.
Tattoo it on your arm. Just write C. They don't know. Well, actually, Mr. Gutman knows calculus really well. So.
Oh, does he really?
Yeah, he was an engineering major.
Crap. I'm
Doesn't
screwed.
mean you remember saying it. Any questions on this one?
I'm gonna get a Mike Tyson tattoo. A big C on my face.
Get it under your eyelids.
Yeah.
Just around my eye.
You can see
So
that on
wait.
the test. Yeah.
You could see that on the test. I wasn't Y squared.
You know what, right?
I took out Y squared. So
What's
I
that?
know it's an X.
Yeah, the y was only to the negative 1 power, which we changed. And the negative we left behind because we didn't really want negative y, we just wanted y. So whenever possible, we'll solve these in terms of y. And this is called a separable differential equation. It's called separable because we've got x and y's mixed together in the beginning, but we're able to separate them. There are other kinds of differential equations called we won't look at these, but in this class, but homogeneous, where the x and y are firmly mixed together.
Firmly.
Yes, in other words, they're part of a function. So if I had like sine xy, I'm kind of stuck there. So you end up rewriting one variable in terms of the other and
What is
solve it that way.
parametrics? Does it have to do with that?
No, parametrics is different. Parametrics is two variables, and they're both related to. They're both independent dependent variables, and the independent variable is time. All right. So any equation that contains a derivative or differential is called a differential equation. A solution to a given differential equation is a function that satisfies the equation. Okay? So, in other words, if we go back here, if we were to take the derivative of this with respect to another variable, then we should get back to that equation. Because you notice that we had a dy in here. So if we were taking it with respect to x, we wouldn't end up with we'd end up with a dy dx anyway. So you should be able to get back to this if you differentiate, but we rarely ever do that. And sometimes we just rarely ever do it. But that solution here, this equation here, is the solution to our differential equation. So we have a differential here, and we want the equation that satisfies this derivative. Does somebody have a question?
Can you go to the
Okay. All right, so here we have another one. So a general solution is a characterization of all possible solutions of an equation. So for instance, we have dy dx. First thing we did is we multiply both sides by dx, and that moves, because we don't want dy dx. We want y's on one side, x's on the other side. Well, there is no x, there's no y here, but we can still have a dy. So if we integrate dy, we get y, and if we integrate 2x, we get x squared. It would be x squared divided by 2, but then the 2 would cancel here. So we'd have 2x squared divided by 2. The 2's would cancel, and then plus c. So notice this is the general solution, y equals x squared plus 2, and that's the equation that satisfies this differential. So y equals x squared is a solution to dy dx equals 2x, since 2x is the derivative of x squared. So there's a more simple example where you can see that the solution to the differential is the equation that satisfies that derivative, that has that equation as its derivative. If we're given an initial condition, so let's say we're given this initial condition here. Y equals 5 when x equals 2, then we can solve for the particular solution. We just plug in 5 for y and 2 for x, so we solve for c. And so now we have the particular solution, y equals x squared plus 1, that satisfies our initial condition there, y equals 5 and x equals 2, and is the solution to this differential equation because it satisfies the derivative. Yeah?
The derivative gets us the slope, or the slope for the change at a certain point, and then dy dx is the change in y over the change. It just clicked.
Oh, good.
I'm pretty sure you went over that like forever.
No, but then it makes sense now.
It makes sense then.
2.
You know what, Russell? I would have looked at the pretty.
And so I'll go through, I left my writing up here mainly so that I could, you wouldn't have to write everything in, so I gave you a printed copy, but the printed copy is too small, let me know. So I'll go through this. All right, so here's our equation, dy dx equals 2x squared. Our first step is to multiply both sides by dx, because we want x's on one side, y's on the other. Okay? And you can't move the dy, but you can move the dx. You can't move the dy because it's in the numerator. But you can multiply both sides by dx. Cancels here. Now I've got dy equals 2xy squared dx. I don't want the y squared on this side because this is the x side. So we'll divide both sides by y squared. So now we have dy y squared equals 2x dx. We differentiate both sides. Okay, so we have dy over y squared. And you can change that probably to like this, y equals negative 2. Dy equals 2x dx. Was this the one we had on the other page? Or
Yes.
Oh, it was the one we had on the other page. Never mind. Sorry. Well, there's all the steps not all crammed in there, so you can see them all. Oh, this one's like looking really familiar. All right, so then we just integrated. So we have negative 1 over y. And so I am showing you that you can add a c to both sides if that helps you. But no, once we solve, we'll combine the c's, because all this is a constant 1 and a constant 2, and it's just a constant. So if you want to be technically correct when you integrate the y here, you could write c1 here, and you could write c2 when you integrate the x, but you can just combine them as a c, because this is a constant. This might be some constant. This might be some constant. Together, there's no constant.
What's the rule for adding c to one side? Like, what does it one from happen?
Well, usually, sometimes people leave the c off of the y side, knowing that we're going to be isolating the y anyway. But technically, whenever it's the indefinite integral, you'd put a c in there.
On both sides?
Yeah, you could put them in on both sides if you want to be technically correct, and then only include 1 at the end.
Do we get marked off if we do it?
They don't.
Probably not,
Well,
no.
doesn't it like not make a difference because even if there was a constant on the other side,
Right.
it could be moved.
Yes, yes. As long as you understand that, it's fine.
Okay.
Yeah. And then we could just, you can flip both sides, right? So you can move them over if you don't like where the negative is. So just another way to solve it. Multiply both sides by y. What happened to my y? Oh, in this case, I did something a little bit different. That's why I wanted to go over this one. So in this case, this is just a different solving. Same answer, but a slightly different solving. So in the other problem there, I multiplied both sides by y and then divided both sides by x squared. This problem here, instead, I raised both sides to the negative 1 power. So if I raise it to the negative 1 power, this now becomes the reciprocal. This becomes 1 over negative x squared plus c, and now 1 over y becomes y. So just a slightly different way to get your general solution. Yeah, did you need me?
Are you going to use computers for finals?
Mm-mm.
Perfect.
Stay with us. Do calculus.
So I need to find out when I'm picking up your guys' computers. Oh wait, yours is easy.
Hey, so yeah. So this is another way to solve that same problem. Okay. So I did give you both solutions. So here, one way you could solve it, and so you don't want to keep multiplying and dividing, is you could raise to a power to move that y into the into the numerator and stop being a 1 over y. Just so long as whatever you do to one side, you do to the other. Well, it's an allowable move. Okay, so here we have dy dx equals x to the 5th. The y's go with dy, the x's go with dx. So all you have to do is multiply both sides by dx. Then you'll integrate, isolate y, and don't forget your c. Okay, I usually add the c at the end myself. So on this one here, we multiply by dx. We have dy equals x to the 5th dx. And then integrate, we have y equals x to the 6th divided by 6 plus c. So it's a nice, easy, separable equation.
Just the linear approximation. Differential equations. We didn't.
Yeah, yes, and a little bit, yeah.
Wouldn't you be able to just do this normally by taking an antiderivative?
But this relates to other things too. So you'll need to know the steps because they'll get more complicated.
Well, no, I'm just saying, just like for this exact one, though.
Yes, yeah.
Just take the normal antiderivative and it'd be correct.
Yes, yeah. Well, not with the dx over here though, because the integral, the antiderivative for dy is y, not dy over dx.
What is the integral?
There isn't one because you can't have variables mixed, which is why we separate them. All right, so here we have dy, another simple one. Dy dx equals 1 over x. Multiply both sides by dx. We integrate. So if we integrate dy, we get y. If we integrate 1 over x dx, we get natural log of x. Do not forget your absolute value bars plus c. Okay? You do need absolute value bars with natural log.
Because the number in there has to be positive, because if it's negative, then it can't work.
Okay? These all have to be defined, so natural log is only defined for positive numbers. So you got to have the absolute value bars in there. It's not necessary if what's in what you're going to be taking the natural log of is always positive. But if it's not always positive, in this case x doesn't have to always be positive, we need the bars. Can't open that one-handed. There we go.
Water bottles, my penis and shit.
If we don't have the absolute value bars, will they mark us wrong?
Yes, if it's a multiple choice and you choose the one without the bars and the bars were needed, yes.
Oh, well, if it's
And-
multiple choice and I see the bars, I'm like,
Or if it's a FRQ, there'll probably be like a point for that. All right, so here we have dy dx equals 1 over 1 plus x squared. Okay? So we need to separate the y's go with dy's, x's go with dx's. So multiply both sides by dx. We have dy equals 1 over 1 plus x squared dx. And then we'll integrate both sides. We integrate dy, we get y. Integrate 1 over 1 plus x squared. Hopefully you recognize that as arctan. So arctan x plus 1. Yeah.
How come if you take the integral of dx, it doesn't equal x, but you take the integral of dy, it equals y?
This would equal. So if I had just dx, that would be x.
How come you have 1 over 1 plus x squared dy? Why isn't there an extra x?
Because this is technically 1 dy. So if I differentiate 1, if I integrate 1, right, I would get y. So 1 dy is y, just like 1 dx is x.
Does that make sense?
If we have an equation and there's a plus 1 in my equation, so I've got a 1 dx, right? So I'm integrating all of those with respect to x. So you always have to integrate with respect to a variable. These are with respect to x. These are with respect to y.
Does that make sense?
Because we're increasing the exponent by 1. So technically y to the 0 is 1. So this is y to the 0, so we increase the exponent by 1, it becomes y to the first. Got another nice simple example here. All right, so dy dx equals negative e to the x. All right, so multiply both sides by dx. All right, I've got dy now equals negative ex to the dx. And integrate both sides. If I integrate dy, I get y. If I integrate negative e to the x dx, I'm going to get negative e to the x plus c. So this equation here, y equals negative e to the x plus c, is an equation that satisfies the differential dy dx equals negative e to the x. In other words, this equation here has this equation as its derivative. Yeah.
Yeah, there is. It's e to the x.
Now sometimes these will look different, right? If I just took the derivative here, I'd get dy equals negative e to the x plus c. I wouldn't have the dx in there, right? But this equation here does satisfy that one. All right, so here's what's a little bit longer, right? So, and a little bit different. All right, so now, again, I get y's with dy's, x's with dx's. So we'll multiply both sides by in this case, I think I moved the y plus 1 first. So we multiplied both sides by y plus 1. That's fine. Then I multiplied both sides by dx. So now I've got y plus 1 dy equals sine x dx. Okay. So now we're going to integrate both sides.
Excuse this interruption. Can we have our wonderful custodians, Juan and Rosalba, please meet Mr. Festrover in the NPR right now. Thank you.
Sorry for the interruption at home. All right, so we integrate y plus 1 dy, we get y squared plus y. If we integrate sine x dx, we get negative cosine x. I put the plus c on one end. I tend to put the plus c with the x. Now, we look at our equation here and we say, okay, let's isolate y or isolate x. We can't isolate y because I've got two of them. So that I can't do that. And I can't isolate x because it's trapped with cosine. So if you can't isolate y and you can't isolate x, isolate c instead. Right? So if you can't isolate y, you can isolate c. Isolate x. But if you can't isolate either one of them, isolate the c instead. All right, so for this particular equation, we're going to keep the c by itself and add 2x to both sides, 2 cosine x to both sides. So now the equation that satisfies the differential dy dx equals sine x divided by y plus 1 would be y squared plus 2y plus 2 cosine x equals c, or c equals. So this is the equation, c equals y squared plus 2y plus 2 cosine x that satisfies the differential. This is our solution.
And if you take the derivative of that, you'll get the dy's and dx's, and when you make it all...
Right, eventually you can get to look like that. Yeah. Yeah. Because
How do you get the value for y? So you have like y squared over 2.
we're just integrating, so we increase the exponent by 1, divide by the same amount. So it's just the power rule.
Okay.
Yeah. So here's a little more complicated one, and we couldn't just get them, couldn't isolate either variable, so we just solved for c instead. So all these involve finding the equations that satisfy some differential equation. And I think I'll stop here, and I guess start a new portion of the podcast so it doesn't get too long. Any one of them? How many? Yeah, I got several examples. So I'm going to stop the podcast, and then I'll come